So, welcome back to the course on architectural design of ICs. So, we are seeing different multiplier architecture. So, in the last class we have seen that means we have seen that array multiplier architecture is also there, that is also based on the fundamentals are that shift and add. Okay. So, there are different type of that means array multiplication. Okay. So, we will see what type of array multiplication is there and how they basically operate and what are the advantage and what are the disadvantages of them. Okay. So, that we will discuss today. So, this array multiplication, the basic thing is that whatever we have learned, that bitwise multiplication and then addition. Okay. So, here suppose I am considering two A and B, two numbers of 4 bit. Okay. At the very beginning, what is happening? I am having this 4 AND gate over here and 4 AND gate over here. That means, if I just do it something like this. So, at that time what is happening? So, if I am multiplying A3, A2, A1, A0 with B3, B2, B1 and B0. So, what I have to do? So, that means initially what will happen? B0 will be multiplied with each bit of this. So, that means now B0 A3, B0 A2, B0 A1 is B0 A0, right. Then that will be 1 bit shift for B1 and B1 will start from here. So, it will be A0 B1 plus A1 B1 plus A2 B1 plus A3 B1. Okay. Then what will happen? This is 1, this is partial product 1, this is partial product 2. So, this will be added. Okay. So, I will get after addition what I will get? I will get sum 4, sum 3, sum 2, sum 1, sum 0. Okay. And then therefore, there will be carry 1 also. Then again in the next what will happen? This I have to start this B2, okay, and B2 will start from here S2 position. So, now what I have to do? This B2 A0, B2 A1, B2 A2 and B2 A3. Then again this I have to add. As there is this 2 position is 0 0, that means now I do not have to consider this 2 particular case, I have to add only this 4. So, then again I can produce this S5, S6, S7, S8 as well as carry. Then again along with this will start from what? This 4th position, that means 1, 2, 3. From S6, then again I have to add this A0 B3, A1 B3, A2 B3 and A3 B3. Okay. So, now S5 competition is already over. Now, after that again I have to do this. So, here what I will get? S9, S10, S11, S12 and then C3 over here. So, finally, I do not have to do this ANDing operation over here, that means all the bit of B I have already done, completed. So, now finally, what will be my output? S5, S1 and S0. So, this is the final product output of this. So, in this manner what I am doing, initially B0 is ANDed with all the bits of A and B1 that are shifted by 1 and all the bits are ANDed with A. They are being added, where this 4 bit adder they are being, that means now they have been done by using this carry look ahead adder. Okay. So, that means now at the very beginning it is producing this 4 bit sum. Okay. So, apart from that, that last sum that is directly coming out, then again with that 3 and carry out, then that is again added with the B2 A3, B2 A2, B2 A1, B2 A0 and then again it is added here over here. then again the carry bit again it is coming over here, the last sum that is coming out from this, and finally I am getting the product something like this. Okay. So, this is the array multiplication where I am using this 4 bit adder which are made by carry look add adder. So, this is carry this CLA means this is carry look add adder. Okay. So, then next what I can do the same thing. So, the same thing what I can do if I use carry save adder. So, instead of that we have used carry look add adder. So, here I will use carry save adder. So, carry save adder means if I just again rewrite this particular equation A2, A1, A0, B3, B2, B1 and B0, then again what is there? That means now A3, B0, A2, B0, A1, B0, A0, B0, right. Then this is A3, B1, A2, B1, A1, B1, A0, B1, right. Then again there is A3, B2, A2, B2 plus A1, B1 plus A0, B1, okay. Sorry, B2, B2. Okay. Then again at this position A3, B3, then again this is A2, B3, this is A1, B3 and this is A0, B3. Okay. Now, you see that for this position there is no addition operation, right, but for this two bit, this is bit because this is ending operation. Okay. This is 1 bit, this is 1 bit. So, for this 2 bit if I want to add, I need what? I need one half adder for this 2, and whenever I will do this half adder operation. So, at that time the carry will be generated and that will be propagated to the next level. That means, if I consider this as carry 1, so then that will come over here. So, that means what? Now, for doing this I need what? I need 3 bit operation, or along with that I have to add this carry 2. Okay. So, that means here you see that for this is the direct P0. So, this is P00. Okay. Then in this particular this if that means if I consider not full adder, using half adder. So, 0 carry in means this is nothing but one half adder circuit, right. So, that means this is half adder if I do not consider this. So, then that carry will again come over here. So, that means now initially what I will consider for this case, I can consider either of these two using one half adder. Okay. So, this is what? This is this P11 means A1 B1 and P02 means what? This is this A0 B2. Okay. So, if I add this A1 B1 A0 B2 A0 B2 in the first using one half adder, that means what? In half adder, then again from this particular half adder circuit, then again that will be added with what? This A2 B0, that means that is P20 along with the corresponding C1, which is the previous carry from the previous stage. Okay. So, this is one full adder cell and it will produce the corresponding, this is S2, and again this half adder or this, that means this half adder carry, then this will be connected to the next, and the carry generated from this, then again that will be connected or that will be propagated to the next. Okay. So, that means what? As I am doing 4 of this addition operation over here, so I will get 2 carry. So, one carry from here, one carry from here, and both of them will be propagated to the next level. Then again you consider these 2 and these 2 along with the carry over here, carry over here. So, that means for this particular case I need what? One full adder considering this P 3 0 and here this is P 2 1 along with the carry of this to this is one full adder cell, then again this along with this is the, that means this again this will generate the carry. Okay. So, then again I need what? The sum of this, that will be passed to the corresponding this A2 B1 sorry A1 P1 to this sum, and this will be the carry in for this particular case. Okay. Then again this will produce what? The sum which will be added with the corresponding P, this is 0 3 and the carry in over here, that is 0, because no further carry is generated from the previous stage. Okay. So, finally, I will get S3 over here and it will generate 3 carry at this point. Okay. So, here you see that this is the half adder case, or this is also considering this case half adder, then that carry is generated. For full adder, this 2 0 is considered in this case along with this sum from this sum and the previous carry. So, it is generating S1 as well as it is producing 2 carry. So, in the next stage, that means for this particular case, so initially what I am considering P03 means A0B3 and P12 means A1B2. Okay. That has been added with 0, then the sum that is added with carry in along with this A2 and B1. Okay. Then it is producing the sum, then again that is added with this A3 B0 and the previous carry is coming over here. So, that means that initially it is 0, the carry in is 0, because I have to add 2 carry which is generating from the previous stage. So, 2 carry from the previous stage. Again, as there are 3, that means stage in this case. So, that means it will produce 3 carry. So, again 3 carry will come over here and that will be considered something like this, in this manner. This is the array multiplication considering the carry save adder. That means, in each stage I am saving the carry and I am just propagating the carry to the next level. So, using that things also I can do. Then what is the corresponding, that means delay for this car, that means what is the critical path for this array multiplication? The critical path is this, that means that is basically coming from this to this to this, then this, then this to this. That means, this is the longest path which I am getting. So, why ANDing? ANDing is basically for generating the P02 or P12. I need one AND gate to generate the corresponding partial product. So, that AND gate delay will also come. Then, as the carry is basically, if I just go back, okay, if I just go back, as the carry is basically propagating from each of these stage. Okay. So, that is why it requires that time as the critical path for this array multiplication. So, in this case, if I consider this, then it is passing from this to this to this to this to, then again this to this to this, something like this. Okay. So, the number of full adder cell it is passing from, that is half adder, then 1, 2, 3, 4, 5, 6 full adder cell. Apart from that, 1, 2, 3, 4, 5, 6, 7. Okay. Then again 7, but here you consider that 2 half adder cells are there. Okay. So, 2 half adder, here how many full adder? 1, 2, 3, 4, 5, 6 full adder. Okay. But if I consider the another path where it is considering 1, 2, 3, 4, 5 full adder and 2 half adder. So, 2 half adder delay can be considered as 1 full adder delay. So, 6 full adder delay in this particular case along with 1 half adder delay and in this path also 6 full adder delay and 1 half adder delay and 1 AND gate delay. Okay. So, the delay was, so the area is, if I consider n bit, so at that time the area will be n star n AND gate. Why n star n AND gate? That means I need to produce that type, that number of partial products. Okay. So, if the number is, that means if x is of m bit and y is of n bit. So, at that time this AND gate requirement will be m into n. As both are of n, so that is why the AND gate requirement is this. Okay. And this is, there is n minus 1 into n number of full adders. Okay. So, why is so? Because I am having this n of, that means this is the multiplier and this is the multiplicand block. Okay. So, that is why I need this n minus 1 into n number of full adder, because I have to add, and that is in a 2D matrix, right. If that is m and that is n, so at that time it will be m minus 1 into n. Okay. And the delay is 1 half adder plus 2n minus 1 into this, that number of full adder delay is the total delay requirement for this particular case. Okay. So, that means this, if I, as this is n cross n, so that is why this is 2n minus 1, otherwise it will be what, m plus n minus 1. Okay. If this, that means y of n and x of m, so at that time this number will be m plus n minus 1 number of full adder delay. Okay. So, this is the critical path of this array multiplication. So, this is the, that means full adder, that means the array multiplication we have seen. So, this that means what we have seen this, okay, in this fashion. So, this is just the, that means some modification to that. This is known as this Wallace tree. So, that means like a tree structure, we are just adding each of these partial products. Okay. So, here each of this is ground, means here you see these are the nothing but these full adder cells, and this grounded means that one of the input is connected to 0. And at the final stage, what I need one 4-bit addition operation, which is basically where the carry is basically rippling. Okay. So, this is the tree structure for doing the multiplication operation, and this structure is known as Wallace tree architecture. There is nothing but the array multiplication considering the CSA. Okay. So, this is, that means this is the block diagram of this array multiplier with Wallace tree. That means here this array multiplication is being done over here, and this final stage addition operation, that has been done through this carry select adder to finally find out the corresponding product bits of this. So, initial bit has been generated from this, and the other that means 60, as this is 32 bit multiplier, 32 into 32. So, that has been generated from this final carry select adder. Okay. So, the final carry select adder has been generated from this. Okay. So, then there is another method of doing the multiplication operation, that is Booth's multiplier. Okay. So, in Booth's multiplier, actually in multiplier what we do? In multiplier what we do? That means what I said, that we basically added something like this. Something like this we do, and based on this, that means what will be these values based on the multiplicand's value. If that bit is based on this, each of this particular bit position, okay, the value of this, I will select what will be the corresponding value I need to add. Okay. So, if this position is 1, so at the time I have to add A. If this position is 1, that means I have to add 8A. If this position is 1, that means I have to add 16A. If this position is 1, that means I have to add 64A. So, finally, what I have to do, based on this finding the ones, I have to add this 16A plus 8A plus A, and finally, I will get 89A. So, 89A means A along multiplied with 89. So, the final results I will get. But in Booth's that means multiplier, what is the problem in this this array multiplication is that we are considering each of this bit position. Okay. So, if I just go back here, each of this bit position we are considering to find out the corresponding partial product. So, the more the number of, that means if I consider, okay, if I consider x of 8 and y of 8. So, at that time the partial products that I need to generate of 8 combination. If this is 16, sorry, if this is 16 plus 16. So, at that time PP 1 to, sorry, 6, this is right, up to 16 I need to generate, and then I need to add. Okay. So, that means now there will be 16 stage which I need to add this, and each of this is basically I have to add. So, something like this I have to add. So, more of this depth means the delay will be more, delay will be more. Okay. So, that means if I consider the word length more, means I am increasing the delay. So, the people have thought that why can't we reduce the number of partial. If I can reduce this depth, that means at the time I can reduce the delay. So, how can I reduce this particular depth so that I can get the benefit or I can reduce the delay. So, that is why people have done what this, people have done this Booth's multiplication. Okay. So, this says that there is a recoding technique, that means the multiplicand that has been recoded. So, how it has been recorded? It is basically based on this base 4 redundant sign digit representation of B. Okay. So, how is that? The corresponding value has been calculated based on this. The position is like this 2 B 2 I plus 1 plus B 2 I plus B 2 I minus 1. Okay. So, that means what? That means what? Based on this particular, and this Booth's multiplication is basically used for sign multiplication. Okay. Signed and unsigned both. So, if it is unsigned number, that also at that time also you will get the correct result. If it is a signed number, at that time also you will get the correct results. So, how it has been recorded? The recoding technique has been done based on this particular equation, where this says that if that is the position is something like this, that is 2 to the power minus of 2 to the power 1, then 2 to the power 0 and then 2 to the power again that is 0. Okay. So, that means now based on this the corresponding recoding technique is the recoding technique is what I said 0 0 0, the operation is basically 0. Okay. This is a decoding technique using this Booth multiplier. If that is 1 0 0, then at that time that will be 2 along with 1, that means negative is 1, that means this will be minus 2. Why? Because what I said, the recoding technique says that is the final, that means this position is 2 to the power 1, then 2 to the power 0, then 2 to the power 0. So, if this bit is 1 0 0, that means this will be minus 2. Then again 0 for 0 1 0 1 0, for 0 1 0, this is nothing but A, okay, or just the 1. For 1 1 0, for 1 1 0, what will be the case? 1 1 0, this is minus 2 plus 1 plus 0 means minus 1. So, here you see for 1 1 0 1 with negative of 1, and in the same fashion for 0 0 1, that is 1, no negative. For 1 0 1, again 1 1 0, for 1 0 1, what will happen? Minus 2 plus 0 plus 1, that is equals to minus 1. Okay. So, for 1 0 1, 1 with negative of 1, for 0 1 1, that is 2 with positive, 1 1 1, that is 0, okay, but 0 means it is 0. Okay. So, based on this, that means the measure, that means the weight which I need to consider, that can be computed using this particular equation. So, the Booth's recoding, whenever we will follow this Booth's multiplier, at that time this decoding table can be formed if you can remember this particular equation. Okay. So, now if we take the example of this, okay, if we take the example of this, so this is the, that means operation which I need. So, if we take one example of this, so at that time that will be much more clear to you. Suppose this is the multiplicand x and this is the multiplier y. So, initially whenever we will do or we will follow this Booth's multiplication, so at that time what I need to do? I need to add 0 at the LSB position. After that what we will do? We will consider this, the combination of 3 over here for the LSB side first. So, for 0 1 0, for 0 1 0, what is the combination? That is plus 1, okay. And then again actually I have to overlap for the last or the MSB of this or the last bit position, I have to overlap. So, that means at that time whenever I will consider the next set, 3 bit set, at that time I will consider from this to this. Okay. So, for 1 1 0, that is minus 1. Again for the next set what I will consider? I will consider these 3, and for this for 0 1 1, that is plus 2. Okay. So, now for x plus 1 means what? That means it will be, the operation is that the multiplicand that will be plus 1. Okay. So, plus 1 means this is nothing but the x. Okay. So, in the next it is just the 2's complement of that. Okay. So, that means in the next that is minus x, and in the next that is plus x plus 2. Plus 2 means that is 2 of x. So, x means what? X means, if from this if I consider, so x means 1 1. So, then minus of x means in 2's complement format, if I just write, that is 0 and then all 1. Okay. For twice of x means what? The 2 0 will be appended at the very last LSB and it will be something like this. Now, I have to add all these 3 for these 3 set, and here what I will get? 0 over here, then 0, then again here 1, then again here 1, then 0, then 0, then 1. Okay. So, this is the final result. What is that? Okay, sorry. Oh, this is not something like this. Actually, I forgot that. Actually, I have to do this shifting operation too. Okay. So, that means at this first position, this is 0 0 0 0 1 1. Okay. So, whenever I am considering this, that means at the time 2 bit shift I have to do, because 3 bit recording we are using, right. So, this minus x will start from this particular position, that is 1 0 0 1 1 1 1. So, this is all 0. So, then again 2 bit shift, and this 2x will be started from this particular position. Okay. So, if I just want to add, then 1 0 1 1 0 1 1. Okay. Again what happened? Sorry, this is plus 2 means this is only 1. Okay. What I am doing? So, that means now it will be 1 1 1 0 1, then again 1 over here, for 1 this is 0 1. Okay. So, now I will get 1 0 1 0 1 1. Actually, this is 2x means not here, what I am doing, I am 4, not 4, this will be 1 1 0. Just 1 bit add, that means 1 0 at the LSB position. If I have to do 4, at that time I will append 2 0 at the LSB position. Okay. I have done that mistake at the time. So, that means now if you see what my point is, that means how many product, or that means partial products now I am generating, though I have considered this y of 6 bit. So, using the array multiplier, if I want to do this, so at that time how much partial products I will get? I will get total 6 set. So, that means now the delay, added depth delay, if I just say, okay, so that will be 6 at that time, 6 partial product set I have to add. So, that means the depth of that will be 6. But here as I have used this boost that means decoding technique, at that time this partial product set that has been reduced to 3 only. So, that means I can reduce the depth. So, whenever I am reducing the depth, at that time I can reduce the delay too. But here at what particular cost? So, initially I need one decoder table for this Booth's decoding operation, or according to the Booth's algorithm I need this decoding table at the very front of this multiplier, or this is basically nothing but the array multiplication. After this decoding, what will be the corresponding partial product generation? So, that it will come and we will see that. Okay. So, this is the technique for this Booth's multiplication. So, here we are considering radix 4. So, that is why we are considering something like this. If you just want to change the radix, so at that time you can consider more of this, that means 4 bit you can consider, and at that time where will be the change? Where will be the change? At that time, at that case, at that time there will be the change in this particular location. So, we will consider more onto this Booth's algorithm, and if I want to change the radix, then at that time what will happen. So, that we will discuss in the next class. So, this is it for today. Thank you.